Welcome back, everyone, to the eCoreAcademy e-learning platform today. My name is AJay back with another Algebra 1 video for you all, and today's lesson topic is all about function basics and evaluating function rules. This is a basis of Algebra 1, and now we're going to be scratching the surface on exactly what functions are and how exactly we can evaluate them to test for whether or not an equation or a graph is a function. A set of data points can also be considered a function as well. But before we jump into this video, please make sure to do 4 things real quick for me. Please make sure to smash that subscribe button, hit that like button on this video, turn on post notifications, and also feel free to comment down below. Also, take a look at the YouTube share button. Utilize that to more easily share with other people that might need help with this certain topic and just to get attention to our channel to help others out as well. We have lots of interesting content on this channel, and we really want to reach out to as many people as possible and make that impact all for free. So, as I was saying, we're going to scratch the surface on functions. I'm going to show you 2 major rules, one for graphing and one for equations and data sets, how to evaluate whether or not they're functions. And then we're going to look at the basis of domain, range, functions, and relations, overall identifying many different types of properties of the graph, one of the bases of Algebra 1. So without further ado, now that you've done all of those things, subscribed, liked, commented, etc., once you've done all those things, let's jump right into the video. All right, so for our first slide, we're going to start off with our basic terms and definitions, just to get you acquainted to this lesson, what exactly I mean by a function, domain, range, and relation. So these are the major 4 terms of this lesson. So these are all about the parts of a function. A relation is a set of ordered pairs that are mapped as x, y on the coordinate plane. Simply enough, it's just a set of points on a coordinate plane that's identified by your ordered pair. So if you have your coordinate plane that goes x, y, your y is your vertical axis, x is your horizontal axis. They both intersect, and now you have multiple grid points in 4 different quadrants that each have their own specific properties. And now that you have those properties, what you can do is you can always plot points on your graph as x comma y, meaning you'd put your x value first, identifying where it is horizontally, and then go up vertically or down vertically to find your y point, your vertical distance from the y-axis. And then you'd write it as x comma y. So merely it's a set of these ordered pair points. Then, of course, we have our domain, which is a set of all x coordinates, aka inputs or independent variables. So it's specifically if you're given a relation or even a function for that matter specifically, a domain is just a set and sequencing organization of all the x points or x coordinates in those ordered pairs. It's also the independent variable, so domain determines what your range is, and your range is a set of all y coordinates. So if you're to have a series of ordered pairs with x, y for all the points on your graph, then all the y coordinates would be organized as your range, and then all of your x points would be organized as your domain. Since your domain represents all x values, we know that x is always the independent variable. Therefore, your range is shows all of the outputs or the dependent variables, what's resulting as a fact of x, whatever x is. And then lastly, what we're really here for, advancing our knowledge off of these 3 major terms, we're going to identify what a function is. And it's a relation, a specific type of relation, so a set of ordered pairs, where each of the domains, so each of the x values given on the graph, is paired with a unique range value, meaning every x value has only one y value. An x value cannot be repeated with another y value. So that means y can go to multiple x's. However, x cannot cheat in this manner. That's how my teachers always taught me. X cannot cheat with multiple y's. X must be loyal to only one y. But in the opposite manner, y can cheat on x and go to multiple x's. But you'll start to feel a little bit more comfortable with that definition once we start looking at our evaluations and our testings for what exactly to test whether or not a graph or an equation or a set of ordered pairs, your data set, is a function. And functions are written as f of x. That's a symbolization of function, where x is the interchangeable value in the equation. So it's merely written as f of x in place of y. So you'd have your f of x equals your equation, and that's in terms of x. So f of x equals, say, for example, 2x plus y. That's your equation. Instead of having y equals 2x plus 1, you would have f of x equals 2x plus 1 in that case. All right, now you might be thinking, Just like I explained to you, I just simply swapped out f of x and y. Why are we calling it f of x? I know the function, it looks fancy notation, looks like fancy notation. The function, the f kind of represents that function, personality, perception in English, in layman's terms. However, why exactly do we use that specific notation instead of y? So I'll explain it to you. So why is it called f of x when it represents the same exact thing as y? And well, f of x is, it actually is exactly the same thing as y in a regular graph equation. So if you're given an equation of a graph, like a linear equation or a parabola, so on and so forth, f of x would merely be in place of your y. Yes, it does have the same value as y, but it's used to stay more organized. That notation doesn't have different value, but it does help you stay more organized when given multiple equations at the same time. So let me give you an example. If you were to have y equals 2x plus 1, but on that very same graph, you're graphing another equation of y equals 3x plus 3. Now, since y is equal to 2x plus 1 and y is equal to 3x plus 3, that means 2x plus 1 has to equal 3x plus 3. However, that actually does not work because you cannot have y equaling two separate values at the same time. So these two graphs are completely different from each other. Therefore, y cannot be the same value. That's why you have to call it two separate values, because technically, notationally, that's incorrect. So you could call this equation over here y. You could call it f of x, function of x. That's a function of x written as f of x equals 2x plus 1. But on the right side, you can call another number. You can another letter. You can call it g of x. Now, g of x has a completely different graph here, and it's not the same value as f of x in this case. So therefore, the notation helps you change the letter here and still make it in terms of x, meaning that x stays consistent all the way throughout. So x stays consistent, but these two letters here are interchangeable, giving it an easier way to actually distinguish between the two equations rather than just using y. All right, now we're going to go on to testing for a function. So in the following few slides, we're going to be testing whether or not a given series of data points or a given graph is a function using our knowledge of function properties. And I'll make you aware of them, such as our domain and range relationship. You can only have one x going to one y. You cannot cheat, so your x cannot have multiple y's at the same time, and I'll explain why that is the case. And lastly, I'll also show you how to input values into a function to also get an output. So we'll start off by looking at the two tests, which is first one's going to be for your equations and your regular points on a graph, using an equation, how to determine whether or not it's a function. And also, secondly, I'll also show you how to input values into a function to get an output. And also, I'll show you how to use a graph and how to actually determine whether or not a graph is a function without the equation. Without even knowing the equation, you can determine what types of graphs are, functions or not, just by a simple test called the vertical line test. All right, so now let's move on to our very first test. And in order to build up on that test, the next slide is going to be telling you about how to actually discover your domain and range. And then, of course, we can move on to our first test. Then for our final test, we're going to show you the graph test. And lastly, we're just going to show you how to, I'm going to show you on one slide how to input values into a function like you would an equation to get your y values in terms of your x. So finding domain and range. So we're going to find the domain and range of this data set. This is very important so that we can organize the domain and the range on both sides. And then utilizing function relationships, we can determine whether or not x is to multiple pairs of y, whether or not it's a one-to-one function. So that I'll get into the next slide, but we're just going to focus on discovering the domain and range of a given set of values, a random set of ordered pairs on the same exact graph. So set A, this is the set that we're going to focus on, and set A consists of 4 different ordered pairs, 0, 2, 3, 1, 9, 6, and negative 2, 3. Now what we're going to do is we're going to start to look at the domain, which is a set of all x values. Now we know that our ordered pairs are always written as x, y. Therefore, the very first number coming in that ordered pair is going to be our x value. So in this case, we're going to collect all 4 x values of this set. And then we're also going to collect all of the range values because it's written as x, y. That's going to be our second value, the one after the comma. So that's going to be our y value. So let's discover what our domain is first. So our domain is going to consist of 4 different numbers. So that's 0, 3, 0, 3, 9, and negative 2. I apologize. So it's 0, 3, 9, and negative 2. All of your x values from the ordered pairs, separating them. And then, of course, on the right-hand side, we have all of our y values, which is 2, are 2. Let me circle these instead. 2, 1, 6, and also 3. Those are all of our y values, our range. And you can always do the reverse to reconstruct the data set. So say, for example, if you're given the domain separately and then the range separately, you can always utilize those values to actually rebuild all of your ordered pairs once they're given in order. So as you can see, 0, 3, 9, negative 2, it's in the same order as 2, 1, 6, 3. It's matching y value in its ordered pair. So you can always reverse this process and reconstruct your given data set. All right, now we're going to find the domain and range of the graph. Should be a comma. Domain and range of the graph. So let's find the domain and range of this here graph. So just to give you guys a heads up real quick, a function is an x paired with a unique y. So that means x cannot have multiple y's. So we're merely just going to discover what the domain and range of this graph is, your equational graph. And then later on, what we're going to do is we're going to utilize that that data set that we're given on this graph, and then we're going to determine whether or not it's a function utilizing this very property here, meaning that the function is paired with y. And that's the only property of a function that we really need to focus on. So another special type of function that you can also come across is a one-to-one. Now we know that x merely has to be paired with one y. A y can be paired with multiple x's, but this one-to-one is a special type of function, which means that one x to one y, meaning that every single x is paired with only one y, and every y is not paired with another x, meaning x is paired to one y, and that y cannot cheat either. So it's a special type of function. So we're given this data set, our graph, which is 3, 2, 4, 5, 5, 7, and 9, 6. We're going to determine the domain and range, and then we're going to identify whether or not it's a function. So on the left-hand side, we have our domain, and this is how we write our domain. This is what we call our different pods. I like to call it pods, your domain and range pods. And in this manner, you can match them with your range values and see if there's multiple repeating x values going to multiple different y's. That's what you're determining here. And then on the right-hand side, of course, we have our range. So 3, 4, 5, 9 is our domain. And then our range is going to be of 2, 5, 7, and 6. So now we're going to pair them together as if we would with ordered pairs. So 3 would go to 2, 4 would go to 5, 5 would go to 7, and 9 would go to 6. Now, the property that we're looking for here is we're trying to see if there are multiple arrows coming out of the same x number, x value of the domain. And as you can see here, there's not multiple arrows coming out of any of these domain values. Therefore, none of the x's are paired with multiple y's, which does make this a function. So yes, this is indeed a function. However, another property that we can also look at is the one-to-one. So just because an x value is paired with a unique y value doesn't mean that y can be paired with multiple x's. So in this case, we could have had 3, 4, 5, 9, and then our range could have just been one value in this case to still make it a function. However, a one-to-one is specifically when one x is paired with one y, and that very y is paired with only one x. So it's going both ways, a one-to-one. And in this case, yes, there aren't multiple arrows coming out of the range, coming to the range. So therefore, it's paired with only one x, every single range value. Therefore, this makes it 1-to-1. All right, now let's move on to the next slide. So now let's continue on the central topic of the domain and range of a graph. And now let's also do the inverse now. Now let's start to look at a graph and try and discover the domain and range. Like I said before, we started off with our equation and our data set. Now we're going to start off with our graph. So there are 2 different tests. One was your one-to-one, your mapping with your pods. It's called domain and range mapping. And we utilize that to discover whether or not a data set was, in fact, a function. And in that case, it was a function, and it was also one-to-one. But now let's also utilize our knowledge of graphs. So we're going to utilize our knowledge of graphs, specifically your visual graphs, and discover the domain and range from them as well. So let's take a look at this equation here. We have this graph. It's a line segment because it has a definite endpoint. Its endpoints are -4, -3, and 2, 4. So let's start off first by collecting all of the domain values. We're going to collect all the domain values from this graph. So we're going to start off by looking at the set of domain values that we have, and you would essentially just take each and every single point on that line. So as you can see here, we have -4, -3, so that would be -4. Here we have -3, -2, so that would be our -3 there. And then we have -2, -1, so that would be -2 in our line. And then over here we have, going upwards and onwards, we have 2 in our value here. 2 going onwards, and then we go all the way up to our value of 4 all the way up here. Sorry, all the way up here at a value of 2 here, all the way 2, 4 as our endpoint. So as we keep increasing, we're going up one domain from -4 to -2 to +2. So that's our set of domain. Now, how can we rewrite that? We don't want to necessarily write out each and every single one of our points, because with a graph, those ordered pairs can get quite large in this case. So we have -4, -3, -2, go so on and so forth until we reach 2. So we would merely write this as a compound inequality, an and statement, saying that x, your domain, is within a -4 and +2. So -4 is less than or equal to x, is less than or equal to 2, because it does include the endpoints. That is your range. That is your domains. That's the set for the domain. And then for your range, to write it more efficiently, we would start off by identifying all of the points. We know it starts with -3 at your endpoint of -4, -3, and then we're merely going up one point all the way from -3, -2, -1, all the way up to 4. So just to condense that, write it more simply, we would start off with our lowest value, our -3. We would say that -3 is less than or equal to x, is less than or equal to 4, because our range goes from -3 to 4. We would look at our endpoints, and then we would determine that the domain and range with those endpoints. That's all we're doing. We're taking our endpoints, taking the y value of both endpoints for the range, and then the x value of both endpoints for the domain, putting the smallest least value to the left, the largest value to the right, and then determining if it's less than or equal to or less than symbols that you're using in relation to your x or your y. I apologize. This should actually say your y here. That should be a y value, because it's in terms of your y in this case. So that's -3 is less than or equal to y is less than or equal to 4. And now let's determine whether or not this is a one-to-one. So because it is a line, and we know that all lines and line segments are all going to be one-to-one. Functions are the best example for a one-to-one function. They never have multiple y's. They never have multiple x's to one y. A line graph a line graph is indeed a function, but it's also a one-to-one function because it is a line. All lines are one-to-one functions. I'll write it here. All lines are one-to-one. All right, now let's move on. Now let's take a look at one of my favorite tests. This has to do with a graph. So once you're given a visual graph, we're going to decide how to actually determine whether or not it's a function. And this is by a simple rule called the vertical line test. This is merely where you're literally drawing a vertical line along a graph, and you're going to determine with the properties of a function graphically, you're going to determine whether or not it's a function. Very simple. Now for the definition of a vertical line test, we're going to utilize the properties of our function, the definition of a function, and that is because every x maps to only one y in a function, a horizontal line splitting a graph should only cross one point. So if you were to draw one simple, that should be a vertical line. I apologize, vertical. So if you're drawing any vertical line across a graph, along a graph, that means that if that graph has multiple points hitting that same vertical line, that means it's not a function. It cannot hit more than 2 points on that same vertical axis of any part of the graph. So it can be drawn on any part of the graph, and if it hits multiple points, it therefore fails the vertical line test. So if I were to show you some simple examples, we have our circle graph on the left, and we have our sine wave, also known as your seismic waves, but in this case, it's going to be your sine waves, which is also has to do with your frequency of sound and vibrations, things like that. And then your circle graph, basically your circle in geometry. So you have your circle graph and your sine wave, and we merely have drawn a vertical line across the circle graph, and we've drawn multiple vertical lines across the sine waves. And as you can see here, the circle is not a function. This is because when you draw a vertical line here on any part of this graph, it actually hits 2 points while crossing the circle. Therefore, it cannot be a function, can only hit 1 point. That's because the x, in this case, if you think about it in terms of ordered pairs, x is going to multiple y's. Therefore, x is also paired with 1y here and 1y here on that same x value, that same exact x vertical line. And then on the right-hand side, we have our sine wave. It is a function because it has no points that are actually repeated for the x, so therefore x is not repeated amongst multiple y's in this case, and it only hits 1 point on any vertical line drawn. So those are just some examples. Now I'm going to go through major examples on showing you generically, now that we've covered what the vertical line test is, and now that you can actually do it very simple, you just have to draw vertical lines and prove whether or not the graph is a function or not. I'm just going to show you general graphs that are actually functions, and in the next slide I'll show you general graphs that are not functions, so that you already know when someone tells you the graph itself and you don't get a visual of it, you'll automatically think to yourself, oh yeah, I already know this, I've covered this before, and I can utilize mental knowledge of it. You can calculate that same knowledge. So first off, we're going to start off with a slanted line here. So this is your common slanted line, just like any other graph, like y equals x. So on a slanted line on a graph would indeed be a function because the red line, your vertical line, does not touch any 2 points on on that line. And then we're going to move on to our horizontal line here. So if you were to draw a horizontal line on a graph, that graph would, if you were to draw a vertical line on any part of that horizontal line, it would not hit multiple points either. So that is also a graph. Then here we have our sine waves, like I covered before. If you draw it on any part of the sine wave, because of the fluid motion, it doesn't repeat any y values for that very same x. So if you were to draw a vertical line, it would only hit 1 point on that graph, anywhere on the graph. Then, of course, we have our absolute value function, which looks like your v. And for an absolute value function, it only touches 1 point at all times. And likewise, your parabola, which is very similar in shape to the absolute value function, except that it's curved. Drawing a vertical line anywhere on this graph, you would also get a function because it doesn't repeat. And finally, we have here, just your scattered data points. So if you have a set of standard data points, that is also a graph indeed. Just because it's not connected doesn't mean it's not a graph. So if you had scattered points, your scattered ordered pairs in the data set, and if none of those ordered pairs are on the same vertical line, if none of them had the same y for their x, they would be a function in this case because they do not cross multiple points, just only 1 point for every vertical line drawn. And then for graphs that are not functions, first example is a vertical line. So if you have a vertical line that goes straight up and down, because a vertical line goes directly across another vertical line. If we were to draw that red vertical line over that vertical line, it would cross on every single point on that vertical line. So it's more than 1 point, and it's not a function. But the true reason for that, which we will cover later on in this course, we've already covered it previously as well, and also other courses. But when you're utilizing your equation for slope, when you're using slope-intercept form, a horizontal line occurs when you're dividing 0 over x. When you're dividing 0 by anything, you can divide 0 by something. However, when x is divided by 0, you cannot divide a value by 0. It's undefined. Therefore, it's not a function. Then we move on to our circle. And in this case, if we were to draw a vertical line through a circle, it hits multiple points as previously covered. Then, of course, if you were to have a line and a point, so if you have one solid line, vertical or even horizontally going, and it also has a point anywhere on the graph. If you were to draw a vertical line that goes through the point and the line, it would determine that it's not a function because that point will have a matching y value for that one given x on the graph, on that line graph. And then, of course, we have our rotated sine wave, the sine wave that's actually shifted to go upwards rather than sideways. As you can see, it hits multiple points on that vertical line. And then, of course, we have a sideways parabola. It's your parabola when y is squared. So your standard parabola goes up and down. It's merely, positioned this way. It's going upwards. Your lines upwards or downwards. That's because of your x values being squared. But of course, in a parabola that's tilted sideways, it's the opposite. Your y values being squared. So a sideways parabola would not work either. It hits 2 points on the graph for the vertical line test. And finally, if you had scattered points that are actually matching do actually have matching y values for their x values. They repeat the same x for two different y's or multiple y's. Then obviously your vertical line test would fail. It would cross through two of those points, two or more of those points, and would not make it a function. All right, now that we're done with our function rules, I'm just going to show you how to utilize a function to actually plug in values into your function and find out what your y values are. We all know, like our general equation, you take your x value, you plug it into your equation, you know the x value, plug it into your equation, you find your y value, and then you're able to graph those points to make your overall line. But I'll show you how to actually evaluate that function. So in a function that is written as f of x, you can always substitute the x for a number and plug it in the equation. So f of x is written in standard form, in your slope-intercept form. So if f of x equals an equation, the equation is going to be in terms of x. Now, if you're trying to find it for a specific number, a specific part of the domain, you can always substitute x for an x value, an integer. And when you do so, if you substitute f of x for f of 2, then you'd plug in 2 for every single point in the equation that you have x. So I'll show you exactly what that means. So we're given this really complex equation of g of f of 2. Now you might be thinking, why are we going this hard? I don't even know what functions are. Well, it's actually something that you do know. You already know how to evaluate your y equals like your 2x plus 1, your slope-intercept form equations. Now we're just going to put this in terms of f of x and your function rules. So we know that we have f of x equals 2x minus 1. That's the first equation we're given. As you can see in this equation here, we have g of f of 2. So since 2 is being directly affected by f is closest to 2, you would start off with 2. So you take 2. Obviously here, that's our second equation on the right-hand side, but we'll get to that. But on f of x equals 2x minus 1, that's the equation we're focusing on. You'd plug in 2 for x in every single part of the equation. So f of 2 instead of f of x would equal 2 times 2 minus 1. You're plugging in x for 2. Sorry, 2 for x. And then you'd simplify that to get that f of 2 equals 3, because 2 times 2 equals 4, and 4 minus 1 equals 3, solving it just like a regular equation. So we know that f of 2 equals 3. Since we know that f of 2 equals 3, we know that we can substitute this f of 2 within this equation for 3. And in this case, that simplifies to g of 3. So now all of this is canceled out. We're merely left with this g of the result of f of 2, and we know that f of 2 equals 3, so therefore we're left with g of 3. So g of 3, we're going to plug in, it's originally g of x here. That's always in terms of x, always, always, always in terms of x. So we now substitute g of 3 for this equation. G of x equals 3x plus 3 was the original equation. We're substituting 3 in this case for everywhere we find x. So g of 3 equals 3 times 3 plus 3. And we get that g of 3 equals 9 plus 3. We simplify 3 times 3 equals 9. And finally, we get that g of 3 equals 12, because 9 plus 3 equals 12. And our final answer would be 12, because now you've solved what g of f of 2 is. We simplified what f of 2 is, and that was 3. Now you calculate what g of 3 is, and that's 12. So 12 would be your final answer when evaluating this function, utilizing your function rules. All right, everyone. So that'll be it for today's video. I hope you guys enjoyed and found this as a very informative, lesson to you all. Very common core Algebra 1. So if you have any questions, you can always reach out to us through our email at eCoreAcademy@gmail.com, or just leave it in the comments down below, and we'll get back to you as soon as possible. Check out our website at eCoreAcademy.org. Feel free to check that out. It's full unlocked access to everything that we offer as an online e-learning platform to help you guys with this curriculum. We've organized it into course study with note sheets and quizzes to go along with each and every single lesson, just like a full course. You just have to go down there and make a free account to get progress checks, and all of the member benefits. Also, check out all of our social media accounts in the description box below at Facebook, Twitter, Instagram, Pinterest, and also TikTok. See what kind of interesting content we have there, and use those mediums to share all of our videos. Also, don't forget, before you leave, please make sure to like and subscribe if you haven't already. Leave a comment down below, as I said before. Share the video, and also check out all the other courses on this platform with all the new teachers, especially my sister Anita, and many other courses like English 1. And onwards in the STEM and English fields and language fields. So feel free to check those out. So that'll be it for you all today in this Algebra 1 video. I hope you guys enjoyed. I hope you guys learned your function basics and can now apply them as we move on throughout this Algebra 1 course. So this has been AJ. That'll be it for now, and I'll see you guys in the next one. Peace.